Hi, my name is Stephanie Heron, and today I'm going to be doing a short tutorial on carbon-13 NMR and proton NMR. So here is the NMR for a compound C7H9N, and for teaching purposes, the actual structure of the compound is here. Technically this should be unknown, but for teaching purposes it is included to give examples of how exactly you would figure out that this is your structure. So first we're going to look at the x-axis. The range at left starts at 200 and goes down to 0. This is in parts per million, and this region is the downfield direction and this region is the upfield direction. So notice the location of all of these peaks. This is called chemical shift, and the presence of functional groups or electronegative atoms in a compound determines peak location. The peaks themselves represent carbon atoms. So we already know that we have 7 carbon atoms and see 7 peaks here. These carbons are all in a different chemical environment since they're all separate peaks. So how do we determine which carbon represents each peak? There's a really helpful table here from Compound Chem, and back to the electronegativity and functional groups, we can see where we should look based on where our shift is. So thinking about our spectrum, we can go back to the table and we can see that we possibly have an aromatic carbon, so a benzene ring perhaps, which would be 5 of the 7 carbons, and a nitrile. So we plug in our benzene ring and our nitrile, and then we need 2 more carbons and 6 more hydrogens. So we're just going to add a CH3 onto 2 carbons. So now that we have a proposed structure, we can match up which carbon is actually representing each peak. And thinking about nitrogen, we know that nitrogen is fairly electronegative. So it would make sense that the carbons furthest away from the nitrogen are going to be the most upfield. And that is indeed the case. Carbon number 2 is the first peak, carbon number 6 is the second peak upfield. And then the lowest or the most downfield peak here belongs to carbon number 5 since it's the closest to nitrogen. And then the second most downfield belongs to the 4 carbon because it's the next closest, or the next closest to nitrogen, excuse me. So then the rest of them can be discovered using the same logic of whichever is closest or furthest from the nitrogen will correspond to the spectrum. So next, proton NMR is a little more complex, but it does look similar. And the easiest way to differentiate which you're working with is to refer to the x-axis. And it's again in parts per million, but it only ranges from 9 to 0 instead of 200 to 0. So again, electronegative atoms will cause a downfield shift. So we see some peaks here, all spread out. And we know that we have 9 hydrogen because based on our carbon NMR analysis, we already have a given structure. So we know we have 9 hydrogens, but we only have 5 peaks. And that is because some of the hydrogens are in the same chemical environment, which is shown to the right here with each of these groups. So we have 1, 2, 3, 4, 5 different chemical environments. So like carbon NMR, here's a table which shows the effect of electronegativity and functional groups on chemical shift. So again, we have an aromatic in this range right here, which does correspond if you factor in the downfield shifting. Something that was not used in carbon-13 NMR is integration, and that is the number of protons in each signal set. So if you have 3, that indicates a CH3 group. 2 indicate a CH2 group, and 1 of course is a CH group, or it also could be an alcohol group as well. So we have 1, 2, 3 here, 1, 2, 3 here, 1, 1, 1. So next there is splitting, which also was not used in carbon NMR. And this uses the number of lines in each signal set to determine which protons are connected to a given carbon. So we conveniently have both the spectrum and the structure. So we will use the N+1 rule. To do this, you pick one hydrogen from each environment and look at the carbon it's bonded to. Then you're going to look at one carbon over and count how many hydrogens are there, not counting the ones that are in the same environment as the one you started with. That number is your N. So then you add 1 to that N value, and this number should correspond to each splitting peak in the graph. So for example, let's take this environment right here. Here's our carbon they're connected to. Go one carbon over, and there are no hydrogens connected. So that's our 1, or that's our N value. 0 plus 1, N plus 1 gives us 1. So we have one peak here. And you can do that with every single environment, and that will tell you which peak corresponds to each group.